In this video we're going to derive the divergence in spherical coordinates. Now in spherical coordinates the x, y and the z are going to be replaced by an angle of phi, which is in xy plane, an angle of theta, which runs up the outside there of the sphere, and a diameter of r. Now we're interested in this small volume element, so we can see that the small volume element, well, it's going to be given by the distance dr times the length along this distance here and the length up here. So you can see that the length up here, well, that's just going to be given by our radius r times our d theta, but the distance along this distance here, well, you'll notice that along here it would just be given by our value of r d phi, but you'll notice that the value d phi actually changes and it goes towards 0 at the z-axis. So you notice as we head up here, this distance here gets shorter and shorter. So it gets shorter and shorter by a factor of the sine theta. So we'll see that that distance then along there is going to be r sine theta d phi. So you can have a wee look at that and convince yourself of that. So that means the overall volume is going to be given by our dr times our r d theta times our r sine theta d phi, which is given by r squared sine theta d phi dr. Now we're interested in flux through all of the faces of this little element here. So I've redrawn the element out and we're going to look at first of all face 1 and 2. Now face 1 is going to be the top face here, okay, that's facing out, and the face 2 is going to be the bottom face which faces in towards the centre of the circle. Now you'll notice I've drawn the normals here as well, so the normal is going to face in the opposite directions. So what we're interested in order to find the flux is we could approximate it by working out what the value of the function is at that point in the direction of the normal, and then multiplying it by the area of the face. So the only component that's in this direction of the normal of that function is the components of the function that are in the r direction. So it's kind of like if you were to find a dot product, and if you were to find I dot I would give us a value of 1, which would give us the r direction, and the I dot j would give us a value of 0, so the phi would disappear, and the I dot k would give us a value of 0, so the function of theta would disappear as well. So I've just written this out then, and I've simplified it, and I've just written the value of the function fr, so that's just the value of the function at that point. Okay, and the point there as well, it's going to be given by the distance r plus delta r upon 2, and you can see that up here. If you see the distance r is actually the distance to the centre point here, and then plus the delta r upon 2 takes us to the top surface. So we'll have a value of the function f of r at r plus delta r upon 2 comma theta comma phi, and then we're going to have to multiply it by the area of that front face. Now you can see the area of the front face is going to be this distance here times the distance along here. Now the distance down here, well, that's going to be it would be our r times our d theta, but it's not the value of r because we've got to get to the front face. It's going to be r plus delta r upon 2 d theta. So that's one of them done here. So I've got r plus delta r upon 2 times our, now I've actually not using the d value, I'm just using the delta, okay. So r plus delta r upon 2 times delta theta, and then we're going to have the same for this distance here. So it would ordinarily be r plus delta r upon 2 times our d phi, but of course we've got to add in our factor of our sine theta there as well. So we're going to have our r plus delta r upon 2 sine theta d phi. So when we put those two together, we're going to have our r plus delta r upon 2 squared delta phi delta theta sine theta. So that's for the flux in the front surface. Now the back surface, It's the same thing again. The only difference is that instead of going forward by delta r upon 2, we're going to go back by delta r upon 2. And also the normal is in the opposite direction, so we're going to have a negative value there. So it's going to be minus f of r minus delta r upon 2 squared, delta phi, delta theta, sine theta. Okay, now we can take that whole thing there, we can do the same trick as in the previous video. We can multiply this whole thing by our r squared delta r upon r squared delta r, and there's no any change in that whenever we go ahead and we do that. But we notice now what we're going to be left with is our value of r squared delta r sine theta delta phi delta theta. So that top line there is now going to be that little volume element there, and that's the reason for multiplying like this, in order to get the volume in the top line. So now, in order to get the flux at a point, what we've got to do is we've got to divide out by that volume element. So we're left with the limit as the volume tends to 0 of 1 upon delta v of the surface integral of the normal component of the surfaces 1 and 2. And you can see then we're going to be left with, well, our delta r is going to get subsumed within this limit here. And when we take that limit there, well, we're going to be left with the partial derivative, so it's going to be partial by partial r of, well, there's going to be an r squared term there because the delta r will tend to 0, so we'll have that r squared term, and we're also going to have the function f of r. And we're going to be left here with the bottom line, the limit there, the delta r will disappear, and we're going to have our 1 upon r squared. So we're going to have this first factor here, 1 upon r squared partial r squared f of r all upon partial r. Now that's face 1 and 2. Now we're going to go and look at face 3 and 4. Now face 3 and 4 are these faces here. So the face that faces up the way here, I'll just get it up a bit. So it faces up the way here. So we're looking in this direction, and face 4 is this one here, this little face looking down in that direction there. So we go through the same process for this one here, and we'll notice that we're now looking at it in terms not of our adding up our small elements delta r. R is going to be fixed. We're interested in looking at it in terms of our delta theta. So you can see there in this instance here, it's these two faces here. So we're interested in the variation with our angle theta, okay, because those will sweep out that volume in that direction. So we're going to have our value of our function theta at theta plus delta theta upon 2. Of course, there's going to be our r and our phi in there as well, but these are just going to be our fixed values. Okay, so we're going to have that value of our function theta. Again, we only left with the phi component because the normal is in this direction, and in that direction, that's the normal in the direction of phi. Okay, so it means that the theta and the r will just disappear from the function f. Okay, so we've left with that value of the function in this direction, and that's at angle theta plus delta theta upon 2. So we'll go up there and we can see our theta is this point here plus delta theta upon 2. We could say is maybe that the back face there. Okay, and we're interested then also in looking at the area element there. So the area in the bottom element there, well, area bottom element is going to be given by our r sine, and it's going to be theta plus delta theta upon 2 times delta r times our delta phi. And you can convince yourself of that as well. If you look at the small element there at the bottom there, then you can see that that volume element there is going to be given by our dr times this distance here, and we know that distance there because it's going to be our r plus delta r upon 2, the sine of the theta d phi. Okay, so we do the same for the back surface as well. And no difference to the back surfaces, we're going to have our distance there is going to be the distance minus, sorry, but actually at the top here, it's going to be the distance here plus our delta theta up in 2, and we'll have our minus delta theta up in 2, will take us down to the bottom plate there. So if we were to then take out the common factors here, so the common factor here is going to be, for both of these, common factor is going to be r delta r times our delta phi. Now we do the same trick again. We want to try and get a volume element at the top, so to get the volume element we have to multiply by our r sine theta delta theta divided by r sine theta delta theta. Okay, so we're not doing anything different by multiplying out by this line. That equals that would cancel out. But now on the top line here, along here, we're going to have our volume. Okay, so that r delta phi times r sine theta delta phi, that's going to be, delta theta is going to be our volume element. So then, in order to get the flux, again, the flux at a point, we take the limit as the volume tends to 0 of 1 upon the delta V. So 1 upon the delta V is this section up here. Okay, and our delta phi is going to get subsumed here within the partial derivative, and we're just going to be left with our 1 upon r sine theta, and whenever you take the partial derivative, it's going to be partial by partial theta over, well, it's going to be our f of theta times our value of sine theta. Okay, so that's the second part of this derivation. Now the final part, we're going to look at sides 5 and 6. So sides 5 and 6 are these sides here. So I'll come up the top. So it's going to be this side here, okay, and then the opposite side there. So this is going to be sitting in the variation is going to be within the phi plane, okay, or if you like the xy plane. So let's go ahead and we'll do that. So again, now we're interested in the f of phi, but we're interested at phi plus delta phi up in 2. So we work out the value of the function there, and then we multiply it by the area. Well, the area is simply the r delta theta times our delta r. So you can see that up here. So the area of this point up here is just going to r delta theta times the value of delta r. Okay, so we do the same on the opposite face as well. We're adding phi minus delta phi up in 2, and you'll note we do the same trick here again. In order to get this into the terms of a volume, we're going to have to multiply by our r sine theta delta phi upon r sine theta delta phi. So it means that in order to get the flux at a single point, so the flux at a point, then we're looking at the limit as the delta V tends to 0 of the surface integral of the normal component of our function. So the delta phi is going to be subsumed here within the, whenever we work out whenever we work out the derivation for the partial derivative. So we're going to end up with our 1 upon r sine theta partial f of theta by partial theta. So that's going to give us our values for the surface 5 and 6. So all we've got to do now is add up all of these three. So when we add up all of the three, we'll get the divergence of the function in spherical coordinates will be 1 upon r squared partial by partial r of r squared f of r plus 1 upon r sine theta partial by partial r sine theta f of theta plus 1 upon sine theta partial f of phi by partial phi. So bit of a long-winded one, some awkward maths, but we'll get there in the end. If you like this video, subscribe, and I'll get you on the next video. Okay, goodbye.